Have you ever wondered how GPS, the Global Positioning System, works? It's a fascinating blend of technology and science, a satellite-based radio navigation system owned and operated by the United States Space Force. But it wasn't always at the disposal of everyone. Initially, it was developed for military use, a tool to navigate the complexities of defense and warfare. It was only in the 1980s that civilians were granted access to this revolutionary technology, and by 1995, the system had become fully operational. The concept of GPS didn't just appear out of thin air, though. It was built on the foundations of earlier systems like Transit and Omega. These predecessors were the stepping stones that led to the development of the accurate and reliable GPS we know today. Now you might be wondering, how exactly does this system pinpoint your location? To understand how GPS works, first, we need to talk about the satellite constellation and triangulation. Picture this, a network of 24 satellites, meticulously designed and positioned to ensure that at least 4 satellites are visible from any point on Earth at any given time. This is what we call the satellite constellation, the bedrock of the GPS system. Now let's delve into triangulation. Imagine you're lost in a city. If you spot a familiar landmark, you'll have a rough idea of where you are. Spot 2 or 3, and suddenly you can pinpoint your location with much greater accuracy. This is the principle of triangulation, but instead of using landmarks, GPS uses satellites. By calculating the distance between you and at least 3 satellites, your GPS device can triangulate your exact location on Earth. But how do these satellites communicate with your GPS device? This is where satellite signals and time difference calculation come into play. Imagine a satellite, high up in space, transmitting signals that zoom towards Earth at the speed of light. Each of these signals carries a timestamp, marking the exact moment it was sent. Now picture a GPS receiver, perhaps the one in your smartphone, catching these signals. The receiver notes the time of arrival and, crucially, the time difference between when the signal was sent and when it was received. But why is this time difference important? It's because this difference, even if it's just a few milliseconds, tells us the distance between the satellite and the receiver. This is possible because we know the speed of light and therefore how far light can travel in a given time. This is where atomic clocks come in. These ultra-precise timekeepers housed in each GPS satellite ensure the timestamps on each signal are accurate to billionths of a second. Without such precision, even a tiny error in time could translate into a significant location error on Earth. So, we have the time, but how does this translate into a physical location? This is where the magic truly happens, in the position calculation. This process might sound complex, but it's surprisingly straightforward. Once your GPS device receives the time-stamped signals from the satellites, it uses the time difference to calculate the distance from each satellite. Imagine drawing invisible spheres around each satellite, with the radius of each sphere being the calculated distance. Your location is pinpointed at the point where these spheres intersect. This is how your GPS device determines your precise location. Now, let's talk about accuracy. GPS is incredibly accurate, typically ranging from 5 meters to sub-millimeter levels. That's like knowing the exact spot on a football field where a coin is placed, and all this from a satellite thousands of kilometers away in space. But did you know that even this impressive system needs a bit of help sometimes? That's where correction systems come into play. These are known as augmentation systems, designed to improve the accuracy and reliability of GPS data, ensuring you're not sent on a wild goose chase. One such system was the selective availability feature. This was a method of intentionally degrading the accuracy of signals, making GPS less precise for civilian use. However, the US government discontinued this practice in the year 2000, making GPS more reliable for everyone. Now here are some unheard facts about GPS. First off, GPS needs a relativity correction. Yes, you heard it right. Einstein's theory of relativity isn't just for physicists. The satellites in space experience less gravity than we do on Earth, which means their atomic clocks tick faster. Without correcting for this, your GPS location could be off by miles. And secondly, GPS has a dual frequency capability. This means it operates on 2 different signals, allowing it to correct errors caused by the ionosphere, an atmospheric layer that can interfere with the GPS signals. So there you have it, the fascinating workings of GPS, always guiding you to your destination.